Polymers are a major component of everyday life. Plastics are made of polymers, and polymers are molecules with high molar masses which have repeating units to them. We describe polymers as being composed of monomers, mono meaning one, and then polymer meaning many. So polymers are made of many monomers. For example, you can see polyethylene here is the result of the ethylene molecule bonding to itself over and over and over again. The length of the polyethylene is independent. That is, the length of the structure doesn't really matter in terms of its properties. You can have a polyethylene molecule 100 carbons long or 1,000 molecules long, and it still has essentially the same physical properties. Some common polymers you can see here. I'm not going to spend much time on them. Polystyrene, you can see, is relatively common, used as styrofoam. Let's see, nylon 6,6, that's used in everyday fabric. Polymers are a major component of the world we live in today. And don't worry about memorizing these polymers. It's just to give you some idea of what they look like and how you would see them based off drawing the Lewis structure. We describe polymers as being made in one of two ways. We have addition polymers, which are made by coupling the monomers using a pi bond between each monomer and changing it into a sigma bond. That is, we take double bonds and we put another molecule next to it, which will cause that double bond to break and attach itself to another molecule. So ethylenes, all the pi bonds or the double bonds are broken to form the polyethylene. We have condensation polymers, which are made by making water. What we do is we take a OH portion of a molecule and have it react with a hydrogen in another molecule. Typically, it's a nitrogen attached to, a hydrogen attached to a nitrogen. But the result is whenever you have a condensation polymer, you're basically making plastic and water. And so it takes two different molecules like diamine and adiptic acid to make nylon 6,6. You can see here that we've got our nitrogen and hydrogen right here being attacked by a OH right here, causing it to cleave. And we get our resulting nylon structure over here and some water molecules. Now, polymers have a range in melting points and boiling points, and that's due in part to different chain lengths or different molecular lengths in the polymer. And so when we talk about polymers on a big scale, a bulk scale, then we begin to talk about how much of the polymer is in an ordered region or how crystalline it is. That is, how much is it behaving like a crystal structure? So if you think about these polymers as strands of thread, when the strands of thread are just kind of haphazardly all over the place, then there's no real crystallinity to them, so there's not a lot of strength. However, if we have these threads all lining up next to each other in the ordered region shown here, then we get a high degree of crystallinity and the strength of the polymer increases. We can see this manifest itself through the melting point. The more crystalline it becomes, the higher the melting point becomes. It becomes increasingly stiffer, increasingly denser, and has a higher yield stress. Now, one thing we can do to help enhance these strengths is by creating what's known as a cross-linking polymer, or adding a cross-linking agent, where we actually chemically bond these individual threads to each other, and that results in a much stronger and more rigid polymer. Cross-linking is used with rubber, for example, to make tires, known as vulcanization. We add sulfur to rubber, and that causes these rubber molecules, which are normally flexible and not very rigid, to become very stiff and hard. Switching gears into nanoparticles, we describe nanoparticles as having properties more like individual atoms than bulk molecules. Nanoparticles are less than 1,000 atoms in size, and typically less than 100 nanometers in length. Nanoparticles, as we can see here, we have a cadmium quantum dot, varying composition, and as we can see, as we vary the amount of cadmium in them, we get different colors of solution, representing the different properties of the cadmium being mixed with the phosphorus over here. So we can create these small particles made of the same elements, but it's the size that determines the color, not the actual combination of atoms.